Dear students, in this section, we will see the working principles of a Francis turbine, its velocity triangles, and we will derive some formulas for the hydraulic efficiency of this Francis turbine, the mechanical efficiency, and the overall efficiency. So, we will try to derive all these things. It will be very simple. I can tell it is just the reverse of the centrifugal pump. In a pump, the input energy is the electrical energy or the mechanical energy supplied to the shaft. In turn is converted into the hydraulic energy by pushing the water from below the ground to the floor wherever you are kept with enough flow rate. So that is the pump. The other way is the turbine. In case of the turbine, we are going to make use of the head and the flow rate of the fluid to convert into is equal to electrical power. So turbine is a device to produce electrical power from the hydraulic energy, because we are seeing the hydraulic turbines. We are not seeing about the steam turbines. We are seeing the hydraulic turbines where the hydraulic energy of the water should be converted into electrical energy. One such device is called as the Francis turbine, and this Francis turbine is the more predominant type of turbine available across the globe for the power production, because it can work for a variety of range of head, namely from 30 meters to 150 meters. We can make use of this Francis turbine since it is able to accommodate a wide range of head. Mostly all the hydel power plants are based on this particular Francis turbine. This Francis turbine, the inlet to the Francis turbine is radial. What is meant by radial? If I have a shaft like this, here I have the runner blades surrounding this shaft, then the water will be entering in all the 360 direction. It is called as radial inlet. It is called as what? Radial inlet. And where the water is going to come? It is going to come axially out. It is going to come axially out. So we can see the water will enter into the shaft, not into the shaft. This is the shaft. So this is the blades. So the water will be entering all over circumferential direction, in the radial direction, in all 360 direction. The water will enter inside these veins and it will leave axially out. And it will leave what? Axially out. So that is the working principle of the Francis turbine. That is the working principle of the Francis turbine. And the velocity triangle of the Francis turbine is just opposite to that of your centrifugal pump. If you know the centrifugal pump already, it will be very easy for us to draw the velocity triangles of the Francis turbine. Or if you know the velocity triangle of the Francis turbine, you can easily draw the velocity triangle of the centrifugal pump. On continuing further, we have taken a single blade, a impeller blade. Now the water is going to come from a higher head. The water is going to come stored in a dam and is going to travel across the penstock and is going to come and hit on these veins. So the inlet to this blade is nothing but my V1. This is nothing but what? My V1. What is V1? Which is coming now? Now the water is coming or the jet is coming. So V1 is called as absolute velocity of jet at inlet. Absolute velocity of fluid or jet at inlet. And we know that any absolute velocity component is horizontal component will give me the real velocity, the vertical component will give me the flow velocity. So if I have the V1 as the absolute velocity, then this is an inclined vector which can be resolved into horizontal value and the vertical value. The horizontal value of this velocity V1 will be equal to my VW1, and the vertical component of this V1 will be what? My VF1. So if I consider this is, for example, if I am going to consider this as theta, then VW1, or I'll calculate cos theta. Cos theta equal to what? Adjacent by hypotenuse. So it will be what? VW1 by V1. So I can get VW1 will be equal to what? V1 cos theta. Similarly, what will be sin theta? If I am going to take sin theta, so it will be opposite by hypotenuse. So it will be VF1 by V1. So VF1 will be equal to what? V1 sin theta. So we can see whenever the absolute velocity is not either vertical or horizontal, is inclined, it can be resolved into horizontal component and vertical component. The horizontal component will give me the real velocity and the vertical component will give me the flow velocity. So I hope you could get those points. So now V1 is the absolute velocity of jet. Since it's inclined, it can be resolved into vertical and horizontal. This vertical component is called as what? My VF1. This horizontal component is called as what? I hope I can erase this Francis turbine to make use of the space. So the horizontal component will be what? My VW1. It will be my VW1. Now, what is our aim? Because of this jet coming and hitting this impeller, the impeller should rotate. The impeller should rotate. Okay. So, what is the rotation speed of the impeller? It is either called as U1 or U2. Since it is inlet, it is called as U1. I repeat once again, the main purpose of this what is coming and hitting the impeller is to rotate the impeller. Then only the impeller will rotate. The shaft connected to the impellers will rotate. This shaft, when it's going to cut with magnetic flux, it will induce an EMF. It will produce the electrical energy or the electrical power. Got it? So, our aim is to rotate the impeller. So, let us say the impeller speed is U1. Whether all the V1 can be converted into U1? No, it's not possible. Only a part of the absolute velocity of the jet will be utilized in rotating the impeller. Okay, so that particular component is called as U1. So from here to here, it is called as what? U1. What does it U1 indicates? The rotation speed of the impeller at the inlet. The rotation speed of the impeller at the inlet. Whether it will be equal to V1? No, definitely it can't be. It can be a part of my will component. Not even V1. It will be a part of VW1 only. The will component all will not be converted into U1. Only a part of VW1 will be converted into what? U1. So now we can join this point and this one, this point. Okay, so this velocity is called as VR1. This is called what? The relative velocity between the absolute velocity of the jet and the impeller speed is called as VR1, where VR1 is the relative velocity at inlet. I will make a note. What is VR1? VR1 is nothing but relative velocity at inlet. What is U1? Impeller or vane speed or impeller velocity at inlet. So what is the formula for impeller speed at inlet? Pi d1 n by 60. Similarly, U2 is nothing but what? Impeller speed at outlet. V2 is the absolute velocity of jet at outlet. U2 is the impeller speed at outlet. VR2 is the relative velocity at outlet. VW2 is the velocity at outlet. VF2 is the flow velocity at outlet. I hope you are more familiar with the terms which are used here. Now, this is the input diagram. Coming to the outer triangle diagram, the flow is going to happen like this, axially out. So, it will become what? Here it is V2. Now, V2 is not inclined. It is vertical. Since it is vertical, there is no horizontal component, which means all the V2 will be converted into VF2. Then which component will become 0? VW2 will be 0. Very good. VW2 will become 0. Got the logic? So, VW2 will be 0. Now, what about the blade speed? The blade speed will be U2. The blade speed will be what? U2. The one which comes between V2 and U2 is nothing but called as my VR2. So, this is nothing but my relative velocity VR2. This angle is nothing but beta. The angle between V2 and U2 is beta. So, the angle between V1 and U1 is alpha. The angle between U2 and VR2 is phi. The angle between U2 and VR2 is phi. The angle between U1 and VR1 is called as theta. That's it. We almost got it. So, this type of vanes generally is a forward vane. So, it will be rotating like this. So, U1 is also like this. U2 is also like this. So, you can see the direction of U2 is also like this. Got the logic? So, we can see since the outlet we are making the flow to happen like this vertically. So, V2 will be equal to VF2, whereas VW2 will be equal to 0. So, any doubt in the velocity triangle in the inlet and outlet? V1 and V2 are the absolute velocity of the jet at inlet and outlet. Since it's inclined, it can be resolved into VF1 and VW1. Out of VW1, a small component of VW1 will be converted into U1, which is nothing but to rotate the impeller to produce the power. This is about the inlet. Coming to the outlet, we are making V2 to be vertical, which means there is no will component. V2 equal to VF2. And U2 will also be in this direction because the blade is rotating like this. So, U2 is here. The component which joins V2 and U2 is VR2. The angle between V2 and U2 is beta. The angle between U2 and VR2 is phi. Blade angle or guide vane angle. So we can see here also, we can see here, it is V1 and U1 is alpha, U1 and VR1 is theta. So with this terminology, we will continue further. Let us now try to derive how much of amount of work will be done by the fluid on the impeller blades. How much amount of work will be done by the fluid on the impeller blades. Okay, that is first we will try to do it. Then we will try to find out the power. Then we will try to find out the manometric efficiency or hydraulic efficiency. Then mechanical and overall. Okay. Now for this, we are using the principle called as this one, rate of change of angular momentum is equal to torque developed or applied. Here it is torque developed. So we are seeing a principle. The principle is that the rate of change of angular momentum will result in development of torque. Or if you apply some torque, it will result in rate of change of angular momentum. Both x equal to y or y equal to x. If you are going to apply torque, it will result in the change of angular momentum. If you are going to have the rate of change of angular momentum, it will result in the formation of the torque. Okay, so this only we are going to take as a basic principle, and from this we are going to derive it. What is momentum? Anyone can tell what is momentum? Yeah, momentum or linear momentum. Generally, if we refer momentum is called as linear momentum, is nothing but the part of mass and velocity. So mass and velocity. Here the which velocity will be useful? The whirl velocity only will be useful. So I should not use other velocity. I had to use VW1. Why not VF1? VF1 is used to calculate the flow rate. If I want to find Q equal to area into velocity. There I should not put VW1. There I have to put the flow velocity. So here is what? Whirl velocity, because that only will give the momentum. So this is nothing but a linear momentum. But I want angular momentum. So how to get angular momentum from linear momentum? So angular momentum at inlet will be given by m into Vw1 into R1. So multiply the linear momentum by radius, you will get the angular momentum. So this is the angular momentum at inlet here. What is the angular momentum at outlet? Can anyone tell what is the answer? Can anyone tell what is the answer? Yeah, you are right. The linear momentum is m v omega 2 or Vw2 into, it's not omega, it's W2 into R2. Up to here is linear momentum. When I am going to multiply with the corresponding radius, it becomes what? The angular momentum. So I have the angular momentum at inlet. Here I have the angular momentum at outlet. Now, rate of change of angular momentum. What do you mean by rate? Anyone can tell what is meant by rate? Yes, any quantity which is divided by time is called as rate. Any quantity divided by time is called as what? Rate. So I am going to have m v w1 r1 minus m v w2 r2 by time. Why I have not used the formula mvw2 r2 minus mvw1 r1? I can take like that also, but the input energy will be more. The input angular momentum will be more. So I have written the magnitude. So inlet angular momentum minus outlet angular momentum by time will give me the rate of change of angular momentum. So further proceeding, we can see here m is common. So m into vw1 r1 minus vw2 R2 by time. Any quantity by time is called as what? Rate. Any quantity by time is called as what? Rate. So here is called as m. The unit of mass is kg. Here the unit of time is second. So the next step, this mass by time will become m dot. What is m dot now? Its unit is what? It's not kg. It is kg per second. It's kg per second. Very good. So m dot is kg per second into vw1 r1 minus vw2 r2. So this is nothing but what? What is the left hand side? The left hand side will be the rate of change of angular momentum will be equal to the torque developed. So torque developed will be given by m dot into v omega 1 r1 minus v omega 2 r2. So I hope you got the formula for the how much of torque will be developed in the impeller because of the hitting of this velocity of the jet. Okay, so this is the formula, we got it. Now we are not happy with the torque. We want to know how much of work will be done by the fluid on the impeller blades. What is work done per second is nothing but power. Work done per second is nothing but what? Power. Yeah, you are right. So I can either call this as work done per second or power. Both are same. Work done per second or power developed. So power developed is the formula you know. Torque into angular velocity. For the power, if it's going to be linear motion, means is what? Force into velocity. If it's going to be angular motion, then it will be what? Torque into angular velocity. I hope all of you know these basics. So if you want to calculate the power for linear motion, it will be force into linear velocity. Whereas if the particular device has a rotation motion, then the power developed will be equal to torque into angular velocity. Now already we have the torque. If I am going to multiply by the angular velocity, I will get the power. I will get the power. Very good. So multiply this torque with the power. So power will be equal to this only into omega. So I will write one more step, not a problem. So m dot into V omega 1 R1 minus V W2 R2 into omega. Okay, so we can take this omega also inside. I can erase it and I can write it, I hope. On continuing further, we can derive the formula for the power. So the power will be equal to m dot. It is not m, it is m dot V W1 R1 into this omega is common to both the terms up to here. Omega is common to both the two terms, so it is omega minus V W2 R2 into omega. Got it? Now what is R omega? Generally we know that V equal to R omega. The relationship between the linear velocity and the angular velocity will be equal to what? V equal to R omega. But here this omega is the angular velocity, so it will make the blade to rotate. So it will result in U1 and U2 because we want the impeller to get rotated because of this whirl component. Yes, I hope you got it. So power will be equal to m dot into VW1. Instead of this R1 omega, I can put as U1. Why U1? Because this V equal to R omega. So instead of V, here is nothing but the rotation of the impeller. So it is U1. Our aim is to rotate the impeller minus VW2. What is R2 omega? It is U2. It is what? U2. But we can see here that V omega 2 equal to 0 from the velocity triangle. From the exit velocity triangle or the outlet velocity triangle, we see that V2 equal to Vf2, which means Vw2 equal to what? 0. So I will strike this term 0. So the power developed by the turbine will be equal to m dot Vw1 U1. So you put a bracket for this term and keep it as 1. And keep it as 1. Okay, I hope you got it. I hope there's no need to repeat it once again. So we got the formula for the power developed by the turbine will be equal to m into V, m dot into Vw1 into U1. That is the power developed by the turbine. Okay, nice. Now let us define what is hydraulic efficiency or manometric efficiency. So we can see here the hydraulic efficiency. So what is the hydraulic efficiency? How much of amount of water is coming and hitting the blade? Because of that, how much amount of the shaft is rotating? So the input is the head available, the manometric head available. The output is what? How much is able to rotate the turbine blades? That is the outcome. Got the logic? So the output power will be this one. How much amount of work is done? What is this power term? This is nothing but called as work done per second. Work done per second is nothing but what? By water on the blades. You should be very clear. What is the work done? Work done per second is by the water or the fluid onto the blades. Then only it will rotate. Okay, so this is the power. Now this power equal to m dot into Vw1 U1. You know the relationship between the weight and the mass. What is the weight and mass? Weight equal to mass into gravity. So mass will be equal to W by G, which means it will become W dot Vw1 U1 by G. U1 by G. What is W dot? It is nothing. It is not the weight. It is the weight per unit time. It is the weight per unit time. So we want to carry on this dot also here. So W dot Vw1 U1 by G. Now what is this formula? Once again the same formula only. The left side is work done per second by water on the blades. Now, I want to take another term. Work done by per second per unit weight. Per unit weight means what? I am making the weight to be unity. Per unit weight on the blades. Which means what? I am making this W dot to be 1. So the power will be equal to VW1 U1 by G. VW1 U1 by G. Okay. So this is nothing but the work done per second per unit weight of the fluid on the blades. Now, as I told you, the hydraulic efficiency is nothing but what is the head available at the inlet. Because of that head, how much amount the blade is rotating. Okay, so the input is the manometric head. How much amount of head is available. The output is what? The power developed per unit weight per second. Or the work done per second per unit weight. So the formula will be what? V W1 U1 by G. This G comes in the denominator now. Now the G comes in the denominator. So we can see here the hydraulic efficiency is given by VW1 U1 by GHM. You can also compare the units. The unit of meter VW1 is meter per second. This is also meter per second. This is meter per second squared. Okay, into meter. Okay, so what will happen? This meter per meter, this meter cancel, second square cancel. So the unit will be unitless. It's efficiency. So that only we are taking work done per second. We should take only work done per second. But why we are taking work done per second per unit weight means then only the unit will get tallied each other and the unit will become unitless. It become efficiency. Then only it will become efficiency. So that is the reason why we are taking work done per second per unit weight. I hope you got it. Dear students, let us now further continue with the mechanical efficiency. The mechanical efficiency is nothing but how much the shaft is rotating. That is the shaft power. Okay, how much the shaft will be rotating. To what? How much amount of work is done on the impeller plates. How much amount of work is done on the impeller plates is given by what? This formula. M dot VW1 U1. But instead of M dot, we are going to put as what? W. W by G into VW1 U1. VW1 U1. Got the logic what I am telling? I have to put a M dot VW1 U1, but here I am putting as what? Instead of M, I am putting as what? W by G into VW1 U1. And generally, when you are substituting the formula in the mechanical efficiency, the shaft power is given in, you have to substitute in kilowatts, which means the denominator should also be in what? Kilowatts. So I have to divide by 1000. Got the logic? I will repeat once again. When I substitute in the formula for shaft power in this equation, here SP indicates the shaft power. In this formula, if you want to substitute the value of shaft power, it should be in kilowatts. Since this is already in kilowatts, the denominator should also be in watts, kilowatts, but it's already only in watts. So in order to convert it into kilowatts, I divide by 1000 here also. So both now become what? Kilowatts. So what will happen now? It will become shaft power into 1000 by W into VW1 U1. This G will go to the numerator. Not only G, this 1000 also goes to the numerator. So shaft power into 1000 into G by W VW1 U1. So this is the formula for the mechanical efficiency. So it is 1000 G into shaft power by W VW1 U1. So this is the formula for the mechanical efficiency of a turbine. The mechanical efficiency is nothing but what? How much the work is done by the water on rotating the impeller, that is the input. The output is the how much the shaft is rotating. How much the shaft is, almost it is having a very good efficiency. Mechanical efficiency will be still higher. So we'll get a better value for the mechanical efficiency. So this is the formula for your mechanical efficiency. Now to get the overall efficiency, how to get the overall efficiency? Multiply the hydraulic efficiency with the mechanical efficiency. I will get the overall efficiency. So what is the meaning? The input is nothing but what? Hydraulic head. The output is nothing but what? The shaft power. The output is nothing but what? The shaft power. We are not going up to the electrical power. We are going up to the mechanical energy. So it is the shaft power. So I am going to multiply both these terms. So what is hydraulic efficiency? We have the formula here. P W1 U1 by G into HM into 1000 into G into shaft power by W into VW1 U1. So we can strike off VW1 U1 U1 G. So finally we will end up with I hope I can erase it here. So we can see here the overall efficiency is given by 1000 into shaft power by W into HM into manometric head. Here you have to be very careful when substituting this formula. The shaft power you have to substitute only in kilowatts, not in watts. I hope you got it. So we now derive the formula for what? The hydraulic efficiency. So these three formulas you have to by heart, or you can derive also. If you don't want to by heart, you just derive and solve the problem. This is the formula for the mechanical efficiency. This is the formula for the overall efficiency. Dear students, we are almost at the end, and we will try to find some mathematical expressions based on the inlet and exit velocity triangles. Let us name the inlet velocity triangle as A, D, B and C. What are the name you can keep? You can even keep A, B, C, D. Nothing wrong in the notations. Now let us take the right angle triangle. The right angle triangle is BCD. BCD. Okay, or we can call as what? DBC. Okay. What is tan theta? Tan theta equal to opposite by adjacent. So opposite is nothing but BC. The adjacent is nothing but what? BD. Okay. So tan theta will be equal to BF1 by what is BD? BD will be equal to AB minus AD. Do you agree with me? DB will be equal to AB minus AD. I'll get what? DB. Okay. So what is AB? I know AB is what? VW1. What is AD? AD is nothing but U1. So I'll get tan theta. What is theta? Theta is the wear angle at inlet. What is phi? The wear angle at outlet. So from this, what is theta? Theta will be equal to tan inverse of VF1 by VW1 minus U1. Now let us check the right angle triangle. Which triangle? It is ABC. What is tan alpha? Tan alpha is opposite. Opposite is BC. The adjacent is AB. So what is BC? BC is nothing but VF1. What is AB? AB is nothing but VW1. So we can see here tan alpha equal to this much. So alpha will be equal to tan inverse of VF1 by VW1. So if you know any three terms, we can find the other term. If you know theta, VW1 and VF1, we can find U1. If you know VW1 and alpha, you can find VF1. Like that. Mostly we can find. If there are four variables and you know the three variables, you can find the fourth one by using these relationships. Okay, so we found what is the formula for theta, what is the formula for alpha. Let us go to the outlet triangle. In the outlet triangle, we can find only phi because beta is 90 degree. So we can see tan phi. What is tan phi? Opposite. Opposite nothing but let us give the name as B dash, C dash, A dash. So the tan phi will be opposite something but B dash, C dash by adjacent is A dash, C dash. So it will become what is B dash, C dash? VF2 or V2. Both are same. By what is A dash, C dash? It's nothing but U2. So we got the value of for phi also. So phi will be equal to tan inverse of VF2 by U2. So we'll be in a position to calculate alpha, theta, phi. There's no need to find beta because beta is already 90 degrees. So these values will also be useful to find the efficiency and other terms given in the problem. So if you know this theory part with the velocity triangle, it's very easy to solve any numerals given in your exam or any competitive exam. I hope you got the logics. Thank you.